Hello everyone, my name is K. Anusha, working as an assistant professor in electrical and electronics engineering in St. Martin's Engineering College. Today we are going to discuss about the power electronic converters. Before going to the power electronic converters, we have to know about the what is mean by power and what is mean by electronic devices. Here, first we are going to discuss the electronics. So electronic devices, we are living in 21st century. In all our lives are rely on the electronics only. Like example, mobiles, laptops, TV, all are the electronic device. Without these electronic devices, we can't imagine our lives. Means we are lives in different, completely different without the electronic devices. To operate that electronic devices, we require the power. So to when we are using the electronic device means we have to operate that electronic device. That electronic device will be work on depends upon the power. So what is mean by power and how the power is generating and transmitting and distribution to our end, means consumer end, how we are going to use the power. Now first will be the power. Power is the product of voltage and current. That power will be how, where it is generated and how it will be transmitted. Here this is the block diagram of the generating of the power and transmission of the power and the distribution of the power. Here generating, transmission, distribution will be the three stages of the power. So here red line will be indicates that generating station. Here we are going to generate the power, and the blue line will be indicates that transmission. By using these transmission lines, we are going to transmit the power to the distribution station, and here green will be the distribution system. And after from the distribution system, we are going to take the power to the consumer, and here black line will represent the consumers. And here how the power will be generated. The power will be generated in different ways. One is by using the thermal power plants, hydel power plants, hydel power plants, hydro power plants, and like wind power plants and nuclear power plants also we are going to generating the power. That mostly we are generating the power by using the thermal power plants, means by using the coal we are generating the power. By combustion of the coal we are getting the heat. By using that heat we are going to boil the water. Whatever the steam we are getting, by that steam we are rotating the turbine, and that turbine is connected to the generator. That generator will convert the mechanical energy into the electrical energy. That is, we are going to generating the power at the generating station. Here in the generating station, we are generating the power if 11 kV. So if we transmit that 11 kV through the transmission lines and the distribute by using the distribution system, we are not getting the output voltage properly what we require, because in the transmission and distribution we have so many losses. We have that losses are environment losses will be there, and conductor losses will be there, like that so many losses will be there. So we have to transmit the power. When we have to transmit the power higher range, due to that losses some energy will be dropped and we are getting the some amount of energy. For that, in the generating station we are going to use the step up transformer. So what is the work of step up transformer? Means whatever the energy generated in the generating station, that will be stepped up by using the step up transformer. If the 11 kV will be generated, we are going to step up that energy up to like 765, 500 or 345, like that, depending upon the generating station. We are going to step up that energy, and that step up energy will be transmitted through the transmission lines. So whatever the transmitted through the transmission lines, that power will be consumed by the substations, that is the distribution substations we are called. In this distribution substations, we are going to use the step down transformer, because here the transmitted power will be the 500 volts, that is the very higher voltage. So we have to decrease that voltage to the some lower levels. So here by using the step down transformer, we are going to decrease the power to the lower levels. From that step down distribution substation, we are giving the connections to the different types of consumers. So here some primary customers will be there, secondary customers will be there, like industrial and some local substations will be there. We are sending that that energy into the local substations. In that local substations, the energy will be stepped down to the 11 kV, 4 kV, like that. That 4 kV will be transmitted to the distributed to the distribution lines to the nearer to the transformer that is located at the nearer to the house. In that transformer, that 11 kV or 4 kV voltage will be stepped down to the 120 volts and 240 volts. So here 120 volts will be the single phase supply, 240 volts will be the three phase supply. This 120 volts will be used by our domestic purpose and 240 volts will be used by the agriculture purpose. Like in this way, the power is generated, transmitted and distributed, and the power is coming to our customer end. So here we are going to use the power to the electronic devices. So here whatever the power coming to our houses, that is in the form of AC. But in some cases, we have to give the power in the form of DC, in the form of AC, but some different frequency level. So for that, we are going to use the power electronic devices. By combination of that whatever the subject is dealt with an power with an electronics will called as a power electronics. Means power electronic deals with how to control and convert the power from one form to another form and how to utilization of that power at higher efficiency. That is mean by the power electronics. And here this is the block diagram of the power electronics. Here this is the source of electric power and it is the electric load, and here power converter. Source of electric power. There are the different types of source of electric power. It may be AC or it may be DC. So it is the electric load. What we are going to drive that load, that is different types of load, resistive load, inductive load and the capacitive load. Different types of loads will be present. So when we are giving this power to the electric load, so we have to transmit that power from one form to another form by using the power converters. By using the power converters, we have to transmit the power from energy source to the load. So now we are going to discuss about this power converters. Our main topic is the power converters only. So what are the applications of the power electronics? Means there are the four different types of applications will be there. One is the domestical applications, industrial applications, aerospace applications and transportation application. Example, in domestic applications, we are using the mobile chargers to charge our mobile. That is on one of the electronic power electronic device, and that is nothing but a power electronic converter. And next one's to operate the AC and TV, we are going to use the remotes, that also power electronic device only, and washing machine. In all these, we are going to use the power electronic devices. And industrials, to run the blowers, fans, pumps, compressors, etc., we are going to use the power electronic devices. And aerospace, to give the power supply to the satellites and aircraft systems, we are going to use the power electronics. And transportation, we all know that battery chargers and subway cars, in all that also we are going to use this power electronics. So by using the power electronic devices, we are going to convert. But what it means by using the power electronic devices, we are going to construct one device. That device will called as a power electronic converters. So power electronic converter is a device that changes electrical energy from one form to another form by adjusting the voltage levels. Means whatever the load will be there, depending upon that load, we require some different levels of voltage level. So whatever the requirement is there, that depending upon that requirement, it converts the energy from one form to another form and adjusting the voltages by using the power electronic converter. For example, we have a DC source, but we have to run the induction motor. We all know that induction motor will be run on AC supply only, but we have the DC. So how we are going to run the induction motor? Means we have to convert the DC supply into the AC supply. That will be done by using the power electronic converters. These power electronic converters are divided into the two types. One is the uncontrolled converters and second one is the controlled converter. So why we are going to divide these types uncontrolled and controlled means here depending upon the devices that are using, means depending upon the equipments that are using in the converters, these are going to divide into the two types, that is uncontrolled converters and the controlled converter. So what are that equipment means that call as a power semiconductor devices. We are calling that as a power semiconductor devices. What are that power semiconductor device? We are also called as a power electronic devices also we can call. So what are the devices? Diodes and transistor family and the thyristor. So when we are using the when we are going to construct the power electronic converter by using the diodes and transistor, that type of converter we are calling as a uncontrolled converter. Means we don't have the control on the output voltage, whatever the output voltage getting from the converter. If we are using the thyristor, we have the control on the output. Whenever we want the output voltage, we can adjust the output voltage depending upon what we want. That will be done by the thyristor. That's why we are calling as the converters designed by using the thyristors is called as a controlled converters. Now thyristor, what is mean by thyristor? Thyristor is also called as a SCR. SCR is nothing but a silicon controlled rectifier. S stands for silicon, C stands for control, R stands for rectifier. So S silicon controlled rectifier. This silicon SCR means silicon controlled rectifier. This silicon controlled rectifier has three terminals. Namely anode, cathode and gate. Here this is the symbol of silicon controlled rectifier, nothing but an SCR, nothing but a transistor. So one is the anode, another one is a cathode, another one is a gate. These are the three terminals of the SCR and it has four layers P, N, P, N. These are the four layers of the thyristor, and by forming the four layers we are forming three junctions, that is J1, J2 and J3, and the P layer, top P layer will be as anode, connected to the anode, and bottom N layer will be connected to the cathode terminal. Gate is connected to the P layer of the nearer cathode terminal. Whatever the P layer connect nearer to the cathode layer, that P layer we are going to connect the gate. So here this is the gate terminal. So how the operation of the thyristor will be there? When we are connecting the supply in between the anode and cathode, means anode is positive with respect to the cathode. At that time junction J1 will be in forward bias, junction J3 will be in forward bias, but J2 will be in reverse bias. Then there is no current flow from anode to cathode, but some leakage currents are flowing, that are negligible currents. We cannot take that as a output current. So at that time the thyristor will be in off state. When the thyristor will be coming to the on state means whenever we are giving the gate pulses to the thyristor by using some pulse generator, we are calling that as a pulse generator. So by using the pulse generator we are generating the pulses, we are giving that pulses to this gate to the thyristor by the gate terminal, that we are also called as gate current. So when we are giving that gate pulses to the gate terminal to the thyristor, the junction J2 will be coming to the forward bias. How it will be coming to the forward bias from the reverse bias means here whatever the layer present at the J2, that will be breakdown, that will called as a avalanche breakdown. So avalanche breakdown is done at the reverse bias junction, that is the J2 junction, then it is coming to the forward bias. Then the three layers come into the forward bias. Then the current starts flowing from anode to cathode. That is the thyristor on state. When if we are reversing the voltage, means anode is negative, cathode is positive. If we reverse that voltage, the thyristor does not conduct, means the thyristor is in off state only, because the thyristor is a unidirectional device like a diode. Like a diode, SCR also unidirectional, both are the unidirectional devices only. But what is the, why instead of diode, why we are using the thyristor, means here diode has some disadvantages, that is it is an uncontrolled device. To overcome the disadvantages, we are going to use the SCR, because SCR is a controlled device. So this is the operation of the SCR. Now we'll see the different types of converters. So depending upon the we know that we have the two types of converters, that are the uncontrolled converters and the controlled converters. In the uncontrolled converters, some different types will be there. Controlled converters, different types will be there. Now we'll see the controlled converters, different types. These controlled converters are the 5 types. One is the rectifiers, inverters, choppers, cycloconverters and AC voltage controllers. So here the rectifier. What is meant by rectifiers? Rectifiers are nothing but an AC to DC converters, and it converts the fixed AC to variable DC. And inverters are also called as DC to AC converters, nothing but it converts DC to AC with variable amplitude and variable frequency. Why we are telling that variable frequency, means here we are giving the DC supply, it has a 0 frequency, we are converting that DC into a AC, means AC has some frequency, it may be 50 hertz is the constant frequency, but by using the inverter, what we require the frequency, we are going to convert that amount of frequency. And the choppers are these also called as a DC to DC converters, and it converts the fixed DC to variable DC. Cycloconverters and the AC voltage controllers, both are called as a AC to AC converters. Both are AC to AC converters. Why we are going to use the two different types of converters, means in one converter we are putting the frequency constant, in one converter we are changing the frequency. That by using the cycloconverters, we are going to convert the fixed AC to variable AC with variable frequency, and by using the AC voltage controllers, we are converting the fixed AC to variable AC without change in frequency. These are the 5 types of controlled converters. Now we'll see the controlled rectifiers. So here this is the block diagram of the controlled rectifier. Here input is the AC and output will be the variable DC. Here we are giving the fixed AC, but we are getting the variable DC. Actually DC has a 0 frequency, it is a pure, we are not getting the pure DC. That's why we are telling that it is a variable DC. So here these rectifiers also divided into the 2 types depending upon the supply that is given to the converter, nothing but an AC to DC converter. So what are the different types of supplies? Single phase supply will be there and 3-phase supply will be there. So depending upon that supply, the rectifiers are divided into the 2 types. One is a single phase controlled rectifier and second one is a 3-phase controlled rectifier. Again, this single phase and 3-phase controlled rectifiers are divided into the 3 types, and single phase will be the 3 types and 3-phase will be the 2 types depending upon the what we are getting the output. So single phase rectifiers are divided into the 3 types. One is a single phase half wave controlled rectifier, second one is a single phase full wave controlled rectifier, and third one is a single phase semi controlled rectifier. And 3-phase rectifiers are divided into the 2 types. One is a 3-phase half wave controlled rectifier, 3-phase full wave controlled rectifier. Now we'll see the single phase half wave controlled rectifier. So when we are discussing that single phase half wave controlled rectifier, that is connected to load. Here the loads are different types. One is the resistive load, inductive load, combination of resistive and inductive plus energy, that is RLE loads will be there. RLE means resistive, inductance and the back EMF, nothing but the combination of three is nothing but an motor. Now we'll see the single phase half wave control rectifier with R load, means we are going to take the resistive load. For that we are going to connect one thyristor and one resistor, and here the single phase supply. That single phase supply is Vs is equals to Vm sin omega t. That three are connected in series, and here whatever the voltage appear across the load will called as a V0, that is output voltage, and the current flowing through the load will call as a output current, that is I0, and the voltage appear across the thyristor will call as a voltage across the thyristor VT. When the thyristor is in off state, at that time only the voltage will appear across the thyristor. Now we'll see the operation of single phase half wave controlled rectifier with an R load. So here one is the thyristor and second one is the resistor and third one is the supply, is all are connected in the series. We know that the thyristor has a three terminals. One is the anode, cathode and the gate. So when we are giving the AC supply to the thyristor, the AC supply has the two forms. One is the positive half wave and second one is the negative half wave. So here it is the positive half wave and here it is the positive half wave and here it is the negative half wave. This is the supply voltage that is given to the thyristor. So when the positive half wave is appeared across the thyristor, what happened? When the negative waveform is appeared across the thyristor, what happened? When the positive half wave is appeared across the thyristor, the anode is positive, cathode is negative. So whenever the anode is positive, cathode is negative, then the thyristor will be in forward bias, but the thyristor will be in off state only because it is a controlled device. So we can control the thyristor to operate. So how the thyristor will be operate in the forward bias? Whenever we are giving the IG current, that is the gate current through the gate terminal, pulses is given to the gate terminal, then the thyristor will start conducting. When we are giving the gate pulses means at an angle alpha. I am assuming that at alpha I am giving the triggering pulses to the thyristors. At alpha I am giving the triggering pulses. Whenever we are giving the triggering pulses to the thyristor at alpha, the thyristor starts conducting and the current flowing through the thyristor to load, that is the output current, and due to this output current flowing through the resistor, some output voltage will be appear across the load. So that output voltage will follows the supply voltage, that is like this. Whatever the supply voltage will be there, total supply voltage will be appear across the load. This is the output voltage will appear across the load. Whenever it reaches the pi, again the anode of the thyristor will be negative, cathode will be the positive, means it is in reverse bias, that the thyristor will be in reverse bias. If the thyristor will be in reverse bias, the thyristor is in off state only. Up to which time the thyristor will be off state? Up to the 2 pi, because the pi to 2 pi the thyristor is, the supply voltage will be the negative. So the thyristor will be off state in this mode. Here the thyristor is on state. When the supply reaches to the 2 pi, again the supply will be the positive, means anode will be the positive, cathode will be negative. Then again the thyristor will be coming to the forward bias, but it does not start. When it start? When we are giving the triggering pulses at alpha. Here already it will be the 2 pi, then we are giving the triggering pulses at 2 pi plus alpha. We are going to give the triggering pulses. At that time, the output voltage will appear across the load, that is, this is the from 2 pi plus to alpha. Here it is the omega t, that is the angular time we are calling. So here output voltage we are appearing crossing the load. So how the output voltage, what is the average DC average output voltage appear across the load? So here the output current will be the same, because here we are using the a resistive load. In the resistive load, voltage and currents are in phase. So we are getting the same waveform, but the magnitude will be the different. Here magnitude will be the Vm and here magnitude will be the Vm by R. So now we are going to draw the derive the output voltage of the single phase half wave controlled rectifier. For that we are going to take 2 pi. 1 by 2 pi is an area by total base. So here how many waves we are conducting? Only single wave, that is the positive. That's why we are going to take 1, and the 2 pi will be the total cycle, that is 0 to 2 pi. Integration of Vs d omega t. Here we are going to take the limits. What are the limits we are going to take? Means whatever the operation of that waveform will be there, we are going to take that that angle only. Here this is the alpha and here is the pi. Then lower limit will be the alpha, upper limit will be the pi. And here we know that Vs is the Vm sin omega t dt. Limits are alpha to pi. Here Vm is the constant term, then Vm by 2 pi. Integration of sin omega t will be the minus cos omega t. Here limits are alpha to pi. By substituting that limits, we are getting minus cos pi, that is value will be the 1. Then Vm by 2 pi 1 plus cos alpha, we are getting the output voltage. Output current will be the V naught by R. And what is the RMS voltage of this single phase half wave rectifier? That is the we are going to take the square root and square of the Vm sin omega t. Then we are getting the RMS voltage of the single phase half wave controlled rectifier, that is VRMS. Root means square value, this is the RMS value. Now we are going to see the half wave rectifier, half wave controlled rectifier by using the RL load. Here these are the different types of converters, half single phase and the 3 phase, and the division of single phase and 3 phase, different types. And now we will see the single phase half wave controlled rectifier with an RL load. Only the difference is the load, that is R and L load we are going to use, and the operation will be the same. But so first we are getting the half wave, positive half wave, then the thyristor will be in forward bias. When we are giving the gate pulses at an alpha, the thyristor starts conducting, current is flowing. But whenever it reaches the pi, the thyristor, the supply voltage reverse, the thyristor will go into the reverse bias. But here mean at the time the thyristor off state, then there is no connection of the supply to the load. But due to the inductor present in the load, the nature of the inductor will be the two. One is it stores the energy and it opposes the sudden changes in current. So at the time of conduction of the thyristor, inductor stores some energy, and that energy starts releasing when the supply is disconnected from the load, that is from pi. So at pi what happened? The inductor starts discharging by changing its direction through the supply to the thyristor to the again to the load. At that time the thyristor will forcefully get into the conduction mode. So that will be the from alpha to pi negative voltage will be appear across the load. Up to which point the negative voltage will be appear means whatever the energy stored in the inductor will be equals to 0. At that point the output voltage will appear across the load, that is the negative voltage, that is this one. Up to some angle beta we are telling. So up to beta we are getting the negative voltage, that energy will be stored in the inductor due to the energy stored in the inductor. Again from beta to pi, 2 pi plus alpha, the output voltage, the thyristor will be in off state because reverse voltage will appear across the thyristor. Again whenever we are giving the triggering pulses, it starts conducting, the operation will be repeated. So here is the voltage across the thyristor. Whenever the thyristor is in off state, at that all time the voltage will appear across the thyristor. Here 0 to alpha will be the thyristor off state, then voltage will appear across the thyristor. From beta to 2 pi plus alpha also thyristor will be on state, then the voltage will appear across the thyristors. And here is the current of that output current will be follows the output voltage, but here negative voltage will be there, but the current will be the positive because current will flows from upper to lower only. And what is the output voltage? What is the output voltage appear across the load? That is the V0 DC average V0 we are calling. So here V0 will be is equals to 1 by 2 pi integration of Vs d omega t only, but the limits are different. What are the limits here? The conduction starts at alpha, but conduction ends at beta. Here not at pi, because due to the inductor the conduction will go to the beta. Due to that we are getting Vm by 2 pi integration of alpha to beta sin omega t d omega t. Due to that we are getting the output voltage V0 is equals to Vm by 2 pi into cos alpha minus cos beta we are getting. So how we are getting? Here it is the minus cos omega t, then by substituting that cos beta, minus into minus plus and cos alpha. This is the output voltage we are getting due to the single phase half wave controlled rectifier. And next one is the R, and the current, output current is equals to V0 by R. By dividing the resistor value to the average output voltage, we are getting the average output current. Now we will see the RMS voltage of the single phase full wave controlled rectifier. That is, we are going to square and root the output supply voltage, that is Vm sin omega t. Then we are going to take the Vm under root of 1 by 2 pi Vm square sin square omega t. By deriving that we are getting the Vm by 2 root pi under root of beta minus alpha minus 1 by 2 into sin 2 beta minus sin 2 alpha. This is the output RMS output voltage of the single phase half wave controlled rectifier with RL load. This is the topic today we discussed. Thank you.